Hey guys, today we're going to look at enzymes pretty closely. So let's just jump right in. All right, so here we go. So when it comes to enzymes, a couple kind of important things that we're going to look at really has to do with reactions and chemical reactions in your body. So I want you to take a few minutes, okay, and I want you to watch this video. This is a TED Ed talk. Watch it on your own, and then come back to the video and we'll pick up. All right, so hopefully you've watched that video. And it kind of summarizes everything that, or kind of gives you an introduction to enzymes as a whole. Things that we want to make sure that we can answer. We want to make sure that we know what the word catalyze means, all right? We want to know what an enzyme is. And hopefully from the macromolecules lesson, you can already tell me, hey, an enzyme is a protein. But when we say what is an enzyme, we also want to talk about how it helps reactions move forward, and we want to be able to describe what happens when an enzyme denatures. So that's our goal. So here's the thing about chemical reactions in your cells. If your chemical reactions stop, then the cell dies, all right? And there are a lot of reactions that happen all the time, okay? There's hundreds and hundreds of reactions that all are happening at once. The problem is most of these reactions, if they're just on their own, they're going to be really, really slow. They're not going to happen fast enough to keep the cell alive. And so the cell needs a way in order to speed them up, right, in order to keep itself running. And so in order to do this, it uses a catalyst or an enzyme. And here's the definition for a catalyst. A catalyst speeds up chemical reactions, and they aren't used up in the process. So you can reuse a catalyst over and over again. Catalyze is the verb form as far as like what a catalyst does. So a catalyst catalyzes the reaction. And when we actually look at what they do, they lower the activation energy of a reaction. So this right here, if I get my pen working, that's a really important definition. And we want to know what this is. What's this activation energy? So this is the graph that shows how a reaction moves through time. So time is down here on the x-axis, and as your eyes go from left to right, time is progressing, right? It's moving through time. So this is on the y-axis. I have the amount of energy that is in play in my reaction. And so let's say we start right here. We have the energy of our reactants. And then down here we have the energy of our products. I can tell right off the bat, this would be an exothermic reaction, which means it's going to give off heat. Give off heat. And I can tell that because the energy of my products, so E sub P, the energy of my products, is lower than the energy of my reactant. So that tells me this is exothermic. Now, as far as the catalyst, you can see we've got two lines here. We've got this dark green line, and we have this light green line. The dark green line is how much energy is required in order to start the reaction without a catalyst. So the distance from the energy of the reactants, which is down here, to the very top of this hill, right? So this is the hilltop. That distance is the activation energy. Now, if you add a catalyst, we can see that the hilltop drops. The hilltop comes all the way down here. And so the activation energy with an enzyme present is much lower than the reaction without the enzyme present. And so requiring less energy allows the cell's reactions to take place at a faster rate and, without consuming so much energy from the cell to get them started. And so the cell is able to keep on kicking. Now, one more thing. Let me clear this out. If you were to look at a reaction graph and it looked like this, okay? Well, this is still the energy of my reactant, but now the energy of my product is much higher. This would be an endothermic reaction. All right, and this would feel cool. I'd still have time down here on my x-axis, and on my y-axis, I'd still have energy. So those are the two different kinds of graphs that we might see. Now, how does the enzyme itself work? Well, an enzyme is a protein, and from the last lecture on proteins, you know that proteins have a very specific shape. All right, the structure of a protein is really important to its function. Its function, if it's an enzyme, is going to be to speed up some reaction. And so basically, here's what an enzyme does. An enzyme, it like provides a table for the cell to work on. That's one analogy. So let me kind of explain that. Let's say I wanted to build a birdhouse. So I have all the tools and all the wood I need to build a birdhouse, but I don't have a table. So now every time I want to work on the birdhouse, I have to like bend down. I have to, turn all different ways. I got to like balance the birdhouse on my knee and knock stuff in. And that's really annoying. And it takes me a lot longer than if I had a table. If I had a table, I would have a place for my reaction to take place, right? I put everything on the table. I work on the birdhouse. I'm not bending all over the place. I can find everything I need. The enzyme, or the table in this case, helps me get my birdhouse done faster. What an enzyme does is it provides a place for two substrates or one substrate to meet in order to react. So if it's one substrate, so let's say this picture, all right, more than likely when this substrate, and the substrate is the thing that fits into the enzyme or works with the enzyme, it's probably going to cut this into two pieces. And I'm going to have piece number one, piece number two are going to leave. I'm going to have two different pieces. If I had two pieces that were meeting on the enzyme, maybe the enzyme is going to help them join together, make a bigger molecule. Either way, the enzyme has to bind a substrate or substrates. Those are the reactants in the reaction that it's helping move forward, in something called the active site. Now, the active site is the part of the enzyme, I'm going to outline it right here, that connects to the substrate. So that's the active site. Once it's in the active site, it's going to bind. It's going to hold on. It's going to sit there tight, okay? And there's got to be something on the substrate that matches the active site of the enzyme. And so there's two ways we describe this. The first one is called the lock and key model. I have a substrate here, right? This is the lock and key model. It's going to match this active site. So again, the active site is always on the enzyme. So there's my active site. And when the enzyme and the substrate meet, they bind tightly. And usually the enzyme actually moves a little bit. And that's going to weaken some bonds. So here we can see that there have been bonds weakened in our substrate. And then they can break away. And I have two products from one substrate. Now, that's if time is going this way. All right. Now, enzymes also can work the other way. All right. So if time was running that way, let's say time was going here, we would call this our substrates. And this would be our product. So depending on depending on how the reactants look, if it's two reactants to make one product, or if it's one reactant to make two products, the enzyme can work either way, right? The important part is to know which way time is running there. That's the lock and key model. The active site right here is only going to fit one substrate, and it has to fit just like a lock and a key. It's like true love, right? There's only one true love. The other model is called the induced fit model. Now, this is a more, I think, accepted model from the data that we have. This is a newer kind of model, but both still have good arguments. But let me move my face out of the way here so you can see what we're talking about. In the induced fit model, here's the active site. Oh, let's see, get this back. So again, my active site is on my enzyme. So here's my enzyme. And to induce something means to make it happen. So this is the I'll change for you, baby, right? It's not true love, it's I'll change. We'll be happy when I change. So the substrate, there's the substrate. It enters the enzyme's active site, And then the active site, in this case, it's closing around the enzyme. It's moving in some way in order to get it to work. Both of them are valid descriptions, all right? We'll use both at different times. I want you to understand that the enzyme and the substrate are interacting with each other, all right? There's movement. There is, these are real molecules. They're real things. They're touching. They're moving around. They're breaking bonds. They're making new bonds. All this stuff is happening in real time in your cells. So when we look at the active site, we can't stress how important that is, okay? So this is a great example of structure, the structure and function relationship. Because if the structure changes, the function will change as well. It won't work as well, all right? And so this, in this case, we have this heart-shaped active site, right? Kind of looks like the Batman symbol without the bottom. Batman. Anyway, I have my active site here, okay? And I have this substrate that's going to fit in that active site. But if something happens to change the shape of the active site, well, then it's not going to work anymore, right? So if you change the active site, or you change the shape of the enzyme, that's called denaturing the enzyme. D meaning the opposite of, and the nature being the normal function. So denature, do the opposite of the normal shape or the normal function. There's two ways that we commonly do that in biology. We change the temperature or change the pH. The pH is the acidity or the basicity of the environment, and obviously the temperature is just the temperature. So in this case, we're heating our enzyme above 40 Celsius, which is pretty hot. The enzyme is stretching and deforming, and now the substrate won't fit anymore. Before I keep going. Something that's interesting about this is temperature, right? If you have a fever, right? Have you ever thought why do I get a fever when I'm sick? Well, the reason you get a fever, one of the reasons, is your body is trying to cook the invader, right? So let's say you have a bacterial infection, and the bacteria has enzymes in its cell too. And so your body says, well, let's raise the temperature. We'll cook this enzyme in the bacteria. The bacteria will die before we do. We'll probably be all right. So your body has a natural defense as far as denaturing enzymes is concerned. One problem with enzymes, they work all the time. And so you don't always want your enzymes working. I'll give you an example. Sometimes you eat a big meal and you need to store that energy. Well, there are enzymes in your body that store energy, and there's enzymes in your body that break down those storage molecules in order to give you energy. So I need a way to turn on and turn off an enzyme so that when it's time to store energy, I can store it. And then when it's time to use the energy, I can use it. But I don't want my enzymes competing with each other. So we have these things called inhibitors. They are molecules that are going to interfere with the enzyme's job. And so an inhibitor slows down the reactions in a cell. Now, there's two different ways an inhibitor can work. It can be competitive, in which case, if it's competitive, it's going to mimic the substrate. So it's going to look the same, have the same shape, have the same structure. So it will fit into that active site, and it will, when it gets in there, it'll block the active site. It can also be allosteric. And if it's allosteric, it's going to bind somewhere else on the molecule in order to stop the enzyme from working. Usually when it binds, it's going to change the shape of the enzyme, and we know that if the shape changes, the function changes. So there are a lot of things there, okay? Make sure you can answer these questions. Catalyze, what's that mean? What's an enzyme? How do they work? How do they help the reaction move forward? What's it mean to denature, right? And we'll talk more about enzymes as the year goes on, okay? So let me back out of here real quick. If you guys have questions, of course you can ask, send me questions, come to the Google Meets, Remind is a great way to get in touch with me. All those things are good. Okay, so I will see you guys in the next video.